Okay, so before the break, we were talking about how many functions there are from set A to set B and how many one-to-one functions there are from set A to set B. So I want us to remember this formula here, this formula. Size of B to the size of A, that's always measuring how many different functions there are from set A to set B. So this is going to help us in our next example, which is number of onto functions from set A to set B. So let's just take a very simple example. Let's say set A has three objects, x, y, z. And set B has two objects, 1, 2. Right. So we can take all functions and subtract the ones that are not onto. So this is the technique that we're going to use. But before we do that, let's just evaluate what does it mean to be an onto function. So if we take a look at this example, if we have x, y, z, and the objects 1, 2, we basically want to use up the objects 1, 2. So for example, we can have x goes to 1, y goes to 1, and z goes to 1. This is one example of an onto function. But if you wanted to count the number of onto functions, we don't have that mechanism to do that. So the best way to do that is, again, to take all the functions and subtract the ones that are not onto. Okay. It's easier to answer whether something is not onto. So for example, if I want this function not to be onto, I can take this arrow away from the 2 and point it at 1. So this is one example of a function that is not onto. There's another example where x, y, and z all point to 2, and that's also not onto. So we take all the functions, which is the size of b to the size of a, and then minus the ones that are not onto, which means x, y, and z. In this case, set A, just write it as set A, goes to only the object 1, and set A only goes to the object 2. We basically have two non-onto functions. So at least in this example, we have 2 to the 3 total functions. So we have 8 total functions, and 2 of them are not onto. So we get the answer 6. All right. So generally, how do we calculate this? So what does a general formula look like for the number of onto functions? So I'm just going to do another example here, which is if we have A is equal to W x, y, z. So if I add another W here, and B is equal to 1, 2, 3. So again, I can attempt to do the same thing, take all the functions and subtract the ones that are not onto. So the ones that are not onto here, we can use the same strategy. So if we had the set 1, 2, 3, I can cover up the 3. So let's pretend that 3 is not there. Okay? And I take A and map it to only the object 1, 2. Or sorry, the set 1, 2. So in a similar way, so we should agree that all of those functions, all of the functions that map A to only the set 1, 2 is not onto. Now we can do the same thing by covering up the number 2 and also the number 1. So A goes to only 1, 3, and A goes to only 2, 3. Right, so I hope you can see that all of these functions are not onto. Now, I hope you can see that there's 3 versions of this. So there's 3 versions times 2 to the power of 4. All right, so why is it 2 to the 4? We have size of B to the size of A. Okay? So 3 times 2 to the 4. So 3 types of functions, each with 2 to the 4. Now, while we're here, I can take all functions, which is 3 to the 4, and subtract this. All right, now the problem with this is that we've subtracted too much. If we subtract all of those functions that are going to set 1, 2, and then set 1, 3, and then set 2, 3, we've actually overcounted some of them. So for example, what about the function that maps A, so W, X, Y, and Z, to only the object 1? So this function right here. All right. So I hope you can see that this function is actually not onto. Okay, but we've actually subtracted this function 2 times. We subtracted it once when we subtracted there, and we subtracted once when we subtracted there. So we subtracted too much. We subtracted that particular function too much. So we need to add that back in. We're going to add back where a maps to only the object 1, a maps to only the object 2, and a maps to only the object 3. Okay, so if we add that back in, then this is kind of like the inclusion exclusion rule, if you remember that from set theory. Now here we have 3, and then the number of functions of each is 1, size of b, to the size of a, right? 1 to the 4. Okay, so I hope you can start to see a small pattern here. We have 3 to the 4, and then the 2 to the 4, and then 1 to the 4. Okay, but where are these numbers coming from? So first, we can look at this 3 as the number of subsets of 2, right? Which means that this 3 really is 3 choose 2. And this is really 3 choose 1, right? Because we have subsets of size 1. Okay, now just to complete this pattern, you can kind of imagine that at the very beginning, all functions is 1 times 3 to the 4, which is kind of like 3 choose 3. Right. So you can see that the first number here is really describing the number of objects that we take from B, right? So in the all functions case, we take all 3 objects from B. In the second case, we take 2 objects from B, and in the third case, we only take 1 object from B, and we count the number of functions of each. So at least in this example, this is our final solution. Okay, now if you look at this equation, you might say, well, as we expand, this is going to get a lot more complicated. And you're right, it's going to get a lot more complicated because the bigger the set B is, the more terms that it's going to be. Okay, so I'm going to write down an equation right now, but don't get too scared of this because we're going to come back and review this and we're going to find a really fast way of computing numbers. But here's a general equation. The size of A is equal to n, the size of B is equal to n. The number of onto functions is given by n to the n, so this is all functions. Okay, so all functions. And I'm going to minus n, choose n minus 1. So B, take 1 value away, take 1 object away. So that was in our previous slide, right? So we had 3 choose 2 here. The number of functions associated with that would be n minus 1 to the m, right? So size of B, the size of A, plus n, choose n minus 2, n minus 2 to the m. And we do minus plus minus plus all the way down until we get to negative 1, n minus 1, and then n choose 1, 1 to the m. This is our final term. So basically, until we've taken all the values, all the elements away from B, until we get down to 1 element. So we do plus minus plus minus. So essentially, if this was written in summation form, this is the summation k equals 0 up to n of negative 1 to the k, n minus k, and n minus k to the m. And this is our equation for the number of onto functions from set A to set B. All right, so don't be worried if you can't remember this. This will be given, or you will have reference to this on the final exam or whenever you take an exam. You will be given this as a formula. So the key question is, when is this thing actually used, right? So in what context would it be used? All right. So again, I want you to remember that the number of onto functions is where B, all the values of B are used at least once, right? So this is the equation that measures that. So let's take a look at a very simple example. All right. I have 6 different sandwiches, and I have 3, well, different kids, so that each kid has to get at least one sandwich. So I want to distribute all the 6 different sandwiches, all of these 6 different sandwiches to the 3 kids. So you can look at this as, I have sandwich 1, sandwich 2, sandwich 3, right, all the way up to sandwich 6. And then I have kid number 1, kid number 2, and kid number 3, and then distributing these sandwiches to the kids. But I want all the kids, right, to have at least one sandwich. I don't want them to go hungry. So I hope you can see that this is a direct application to our equation from before, right? So there are m, now remember m is the size of A, and our n is the size of B, so in this case it's 3. So we just plug it straight into that equation. The summation k equals 0 up to 3 of -1 to the k, and then n is 3. 3 minus k, and then 3 minus k to the 6th to the n. And this is it. That's the final answer. Now, you'll find that if you actually expand the summation, that you'll get the answer of 540. Okay, so this is 540 ways to distribute the sandwiches. Okay, but how did I come up with the answer of 540? It turns out that there's actually a very fast way to calculate it. So if we go back and we consider, this is the equation for the number of onto functions, okay? Which means we have m objects in A and n objects in B, and we're distributing all the objects in A to the object in B, but at least one. So every one of the outputs have to have at least one input that is coming in. Okay, so let's expand on this idea. So let's say that we know that the answer here is 540. And I want to answer another question. So sorry, I'm going to just copy some of this over. And I'm going to copy some of this over. All right. So how many ways are there to give 6 different sandwiches to 3 kids so that each kid gets at least one sandwich? And the answer was, as we said, the number of onto functions from 6 objects to 3 objects. All right. So what if we answered a different question? Okay. So another question, how many ways are there to put 6 different sandwiches, so same distribution, into 3 identical bags? So this time we don't look at 3 different kids, but we look at identical containers. Okay, so identical containers so that no bag is empty. So what's the answer there? Okay, so I want you to see that when we're distributing an object, so if I distribute, let's say earlier I had kid number 1, kid number 2, and kid number 3. So let's say I gave kid number 1 S1, S2, and I gave kid number 2 S3 and S4, and I give kid number 3 S5 and S6, right? So if these are identical bags, right, then this distribution would be the same. Kid 2 was here, kid 1 was here, and kid 3 was here, right? Those are the exact same distributions, right, because they're now identical bags. I can list out 3 factorial of the same distributions, right? So K1, K2, and K3 can be reorganized in 3 factorial different ways. So the short answer here is, if we have identical bags, then we have too much order. So the answer is 540 divided by 3. We divide off this order because every distribution would have been repeated 6 times because these kids are different, just because of the fact that these 3 kids are different, okay? But I want you to see that in this question, that these 2 questions on the left and right are the same question The only thing that's different is that we have identical bags here, and the three kids are non-identical, are different, okay? But in both situations, we have 6 different sandwiches, and each bag or each kid has to have at least one sandwich. Okay, so that's key. So the answer on the right-hand side is 540 divided by 3 factorial, which is the size of B, the size of the output. All right, so let's see if we can summarize all of that. So if I distribute m distinct objects into n distinct containers, so this is like our first example, right? Giving 6 sandwiches to 3 kids, right? So they're distinct, different containers, so that each container has at least one object. So this is really nothing more than onto functions. So this is nothing more than an onto function. Okay, this one, number of ways to distribute distinct objects, n distinct objects, into n non-distinct containers, which is identical containers, so that each container has at least one object. So this, we said, is the onto function. But then I divided by n factorial, which is the size of b factorial, the number of outputs. Okay, in fact, this leads to this equation down here. So you'll notice that on kind of most of this looks like the onto function, with the exception of that 1 divided by n factorial. All right, so if we have this, then we're basically answering the second type. Okay, so if we call this type number 1 and type number 2, right? This equation, the Stirling number of the second kind, is really answering type number 2, question type number 2, which is the number of ways to distribute m distinct objects into n non-distinct containers. In fact, this is such a famous number that we have a special name, S of mn. Okay, so S of mn, I'm going to explain when we come back after the break, but just to let you know right now, there's 2 new types of counting problems that we've encountered. Okay, this type 1 and type 2, and they're both very much related to onto function. Okay, so right now I'm going to stop and take a break, and when we come back, we'll discuss the significance of the Stirling numbers of the second kind.